form as the gravity of matter can overcome the tremendous heat. These will become the galaxies we see today. This is important and a bit weird, so I'll get back to it. The next big event happened in the universe was at the ripe old age of about 380,000 years. Up to this point, electrons couldn't bond with the atomic nuclei sitting around. Every time they did, it was so hot that random photons
Or if it's 5 and I'm out of school, you guys can run past my house and I won't fucking lay there in a bikini.
It had cooled enough that the electrons could combine with protons and helium nuclei, becoming stable
Because I need
neutral
no
atoms for the
cameras.
very first time.
Don't play.
We call this moment recombination. This was
I can't wait for the summer, bro.
Free electrons are really good at absorbing photons,
I'm gonna go
absorbing
on
light.
runs,
When the universe was still
as long as I
iron,
don't run past
prior
everyone
to
I know, so.
recombination, it was okay.
No, you're gonna come back. You're gonna come past my house.
Electrons sucked it up. But after recombination,
We'll go to your
electrons
house
were
and then you
free
can
to
run
fly.
with me.
The universe became
Or we're gonna just
transparent.
like spend
Why
time
is
or
this
something.
important? Because the light emitted at this time is what we see as the cosmic microwave background
And then
today. Those neutral
I'm
atoms
gonna
emit
swim,
light. They were as hot as a red dwarf star. Those photons have been traveling ever since, fighting the expansion of the universe, redshifting into the
So far, I
microwave
have
part of the
$25
spectrum.
in my
And
savings
today,
account.
all
I need to
over
save
the
up
sky.
until
I got $2. I had a
Predicted by the Big Bang model, has been on its journey
I need to save up
for
until my
almost
birthday and then transfer
13.8
like
billion years. This
a
light
little bit
is
more than half
incredibly
that money
important because it
into
tells us
my
what the
debit
universe
card
was
so that I
like
can pay
not
to get
long
my
after
own
it
stuff
formed.
at
For example, that light
Mall of
looks
America.
almost exactly the same everywhere you look in the sky. It looks smooth. That tells us that matter was very evenly distributed everywhere in the universe at that time, and also that all the matter had the same temperature. If there had been one spot that was denser, lumpier, then it would have been hotter, and we'd see that in the background radiation as a patch of bluer light. That's pretty weird. When you look at the background radiation from opposite sides of the sky, you're seeing it coming from opposite ends of the universe. Even back then, those regions of the universe were separated by vast distances, and had plenty of time to go their separate ways, change in different ways. They should look pretty different, but they don't. As telescopes got better, very tiny variations in the light were found, but they were really teeny, only a factor of 1 in 100,000. In other words, one part of the sky may look like it has a temperature of 2.72500 kelvins, but another spot is at 2.752501. The universe had lumps, but they were far, far smaller than expected. Something must have happened in the universe to force it to be this smooth, even hundreds of thousands of years after the Big Bang. This led theoretical physicist Alan Guth to propose a dramatic addition to the Big Bang model. At some point in the very early universe, the expansion suddenly accelerated fast. For the tiniest fraction of a second, space inflated hugely, far faster than the normal expansion, increasing in size by something like 100 trillion times. We call this super expansion inflation. It sounds a little arbitrary, but it actually has quite a bit of physical foundation now.
I want to eat it.
In a sense, it's like one of the phase changes of the universe that happen in that first fraction of a second, dumped huge amounts of energy into the fabric of space-time, causing it to swell enormously. Inflation explains why the universe was so smooth at the time of recombination. Space expanded so rapidly that any lumps in it were smoothed out, like pulling on a bedsheet to flatten out the wrinkles. Inflation explains several other problems in cosmology as well. And although the details are still being hammered out, the basic idea is almost, pardon the expression, universally agreed upon by astronomers. The fluctuations we see in the background below now were actually incredibly small perturbations in the fabric of space at the time of inflation, which got stretched by inflation to macroscopic size. These denser spots were seeds, eventually growing even more, their gravity attracting flows of dark matter. Normal matter collected there too, condensing, eventually forming the first stars about 400 million years after the Big Bang. Eventually, those teeny little bumps from the beginning of the universe became galaxies and clusters of galaxies, now tens of billions of light years away. Our own galaxy, our own piece of the universe, started the same way, as a quantum fluctuation in space 13.8 billion years ago. Now look at us. How's that for an origin story? There are still many unanswered questions in our understanding of cosmology. What's dark energy? What was the role of dark matter in the early universe? Where did the universe come from in the first place? Are there more universes out there, hidden away where we can't see them? If time and space started in the Big Bang, does it even make sense to ask what came before it? Or is that like asking what's north of the North Pole? We don't know the answers to these questions, and trust me, there are thousands more just like them. But here's the fun part. We might yet be able to answer them. After all, Even asking if the universe had a beginning, let alone what happened between then and now, was nuts just a century or two ago. Now we have a decent handle on it, and our grip is getting better all the time. Science! Asking and answering the biggest questions of them all. I love this stuff. Today you learned that the timeline of the universe's history can be mapped using modern-day physics and astronomical observations. It started with a Big Bang, when the universe was incredibly dense and hot. It expanded and cooled, going through multiple stages where different kinds of matter could form. It underwent a phenomenally rapid moment of expansion called inflation, which smoothed out much of the lumpiness in the matter. Normal matter formed atoms between 3 and 20 minutes after the bang, and the lumps left over from inflation formed the galaxies and larger structures we see today. Crash Course Astronomy is produced in association with PBS Digital Studios. Head over to their YouTube.
Okay, so the Big Bang. The important things that we want to take away from it, and this stuff is in Canvas, so you can read through this stuff in more detail, but 13.8 billion years ago, this is where physics comes in, that's how they do it, or how they calculate that. So there was a dense point, and some sort of collision happened, and everything started to spread out and cool off, and it cooled off enough that actual particles were able to form. So the first things that formed were basic elements, and particularly hydrogen and helium. So you guys want to remember those two. So then nebulas form, right? So a nebula, the colors come from the way that light refracts through those different elements. So you can see like how bright and colorful that is. That's what you're seeing. All the nebula is gas and dust, and it's light reflecting off of that. So nebula, they were leftover material from the Big Bang. And if you just picture it like all this stuff, nebula burst stars, right? So that star happens, but it doesn't take all of the stuff that was in that nebula. There's still other things around. So that's why it can form planets as well, because those other things in orbit, or all that matter in orbit, is still going to continue to be attracted to itself. So this is the important vocabulary word for today. It's accretion. So it's the process of particles sticking together. So if you think about like a snowball or anything, is a really good analogy. You start with one snowflake, and then a few more stick together, and then a few more, and it just keeps growing and growing, and the bigger that it gets, the more dense it is, right? So this diagram kind of shows it when we're talking about the formation of the planets. So all you need to remember about this is what the process looks like. So it looks like we start with dust, and then the stuff comes together, and it forms something small, and it continues to attract more and more things to itself, and gets bigger and bigger and more substantial and more dense. Okay? And it's the same thing with birthing stars. Got all these little diagrams in there, but you can just see how it starts from just a cloud into something that is very defined and has specific borders. So when they start, nuclear fusion is what causes the sun to quote unquote shine. That's the process that's happening inside the star. That's an important thing for you guys to remember. So we figured the sun formed about 4.6 billion years ago. It was from the collapse of a nebula. Planets, similar process. So that's that leftover material formed into the planets. Our rockier planets are closer to the sun, and then we call the ones Like the ones at the end, those larger ones, the gas giants. And we're gonna talk next week when we start out our solar system here. We're gonna talk about each of the planets individually and learn what kind of differences there are between